All right, so this video, I know the section's called Rolle's theorem and mean value theorem, but I want to focus on Rolle's theorem, which actually is just a very specialized case of the mean value theorem. So there's a warm up here that we may do at some point as a warm up, but I want to start our video down at the actual definition of what it is that Rolle's theorem is saying. Okay, so the Rolle's theorem says, if you have three certain conditions, so if you have a function, so if f of x is continuous on some closed interval a to b, and again, remember the importance of being continuous and closed for having an extreme value. So if f of x is continuous on the closed interval, differentiable on the open interval a to b. So other than the two endpoints, we don't want any cusps or any vertical tangent lines. So f of x is continuous on the closed interval, differential on the open interval, and if f of a equals f of b. Okay, so like your starting endpoints, your f, like your y values must equal each other. So if you get just like a little picture of what that might look like. So there's my x-axis, there's my y-axis. So if these things are all true, so let's say this is A, let's say this is B, and it doesn't really matter where it starts, but if this is where it starts, then there's your f of A. But then f of b would also have to have that same value, right? So they'd have to be equal. Okay, so whatever you want to do, make it up here or come down here or whatever, right? So it's continuous and smooth. Okay, so f of x is continuous on the closed interval, differentiable on the open, and if the two y values of our interval are the same. So those three conditions exist. Okay, then there exists at least one, could be more, but at least one. Then there exists at least one c value on the interval a to b. And actually it's an open interval because we're talking derivatives here. On the interval a to b. So somewhere along here there's a c value. Okay, so somewhere, I don't know, pick this guy here. Right there. Somewhere there's a c value, okay? Then there's just some c value in interval a to b. Oh yeah, such that the derivative of that c value equals 0. And so there's our link into into extremes, because we know that if you're a critical value, your derivative is 0 or undefined. And if we restrict it to being completely differentiable, then we know that you can't have an undefined derivative, so it's 0. So there's always at least one. And so in fact, we actually can find two in this particular case. Like my c value could be there. And if I clone this, oh, I thought I could clone it. Yep, there it is. There's another c value, right? If I could drag that. Right. Oh, okay. Try one more time. Right here. Right. So there are actually two, because there are two spots where there was a horizontal tangent line, aka its derivative was equal to 0. Boy, this is just just getting warmed up here. So trying to wake it up out of its Monday, so to speak, since that's the day I'm recording this. Okay, so those are our two c values. Now, it doesn't say what they are. It just says that they exist. So this is known as an existence theorem. Like, you have to go find them. It's just guaranteed that they are there. And so that's kind of what Rolle's theorem talks about. And again, it's really a direct relation to extrema, because these 0 derivatives are going to be your critical values. So you're always going to be guaranteed at least one if you start and end the same y value. So that's kind of the key there. So let's look at an example. Okay, so verify the conditions of Rolle's theorem. So that's important. There are 3 of them. And then find those values, right? So it doesn't have to be a huge proof. And in fact, you just really kind of had to state things just to make sure that you've checked off those three things. So I mean, it's just a polynomial. There's nothing funny going on there with dividing by 0 or square rooting negatives or anything like that. So I could just say, yes, f of x is definitely continuous. I've checked on the interval -2 to 2. I know it's a polynomial. I know my function is differentiable because it's smooth in terms of the curves. There's no absolute value, right? There might be a cusp there. So it's differentiable on the open interval. And then we got to check what is f of -2 and compare it to f of +2, because those are our endpoints, to make sure that they are equal. So -2, well, I'm going to already observe this is an even function. So whether I put a negative or a positive, it will be the same. That's 16 minus 2 times 4, which is 8. Or it's 16 minus 2 times 4, which is 8. So f of a equals f of b. It's differentiable on the open, and it's continuous on the closed. So therefore, I know that thus Rolle's theorem applies. So Rolle's theorem applies. So that means there's some c value between -2 and 2 whose derivative is 0. So now we find it. So how do we find it? We just solve the equation. We set the derivative equal to 0. So we set f prime of x equal to 0, and we solve for x. So derivative would be 4x cubed minus 4x set equal to 0. Let's factor out a 4x for sure. So it leaves me x squared minus 1 equals 0. And then that factors further, x minus 1 and x plus 1. So then I can check when is that 0? Well, x equals 0, x equals 1, or x equals -1. And notice there's always at least 1. And this time I got 3, and all 3 do exist in that interval. So then I could say my c values that were guaranteed by Rolle's theorem are c equals 1, 0, or -1. All of those values, have a derivative that is equal to 0. Okay. You do another one, right? So again, verify the conditions of Rolle's theorem apply to this function. And again, a square root, so I'm a little bit concerned because of the square rooting in negative value. But on this particular interval, nothing to worry about because all of those values would keep it positive. So I definitely know that f of x is continuous on the given interval, right? And that's really important that we state that because it's not continuous everywhere, but it is continuous there. F of x is differentiable on the open interval, -4 to 0. And again, the only issue would be at these endpoints where there had been a cusp. So like at -4, there would have been a cusp, but it's okay because it's an endpoint, so it doesn't count because I'm on the open interval. And let's check f of 0, and let's check f of -4 to see if they're the same value. So putting 0 in, is get 0. And same thing with -4, we get 0. So we checked all 3 things, and because all 3 things are satisfied, we know Rolle's theorem applies. Now, again, all that tells me is that somewhere between -4 and 0, right, that there are values whose derivative is equal to 0. Right, that's exactly what Rolle's theorem says. So we need to find those values by setting the derivative equal to 0. So we set f prime of x equal to 0 and solve for x. Now this is actually a product rule, so be careful. So the derivative of x is 1. Leave the square root of x plus 4 alone. Now leave x alone. The derivative of a square root would be 1 over 2 times that root. And then chain rule with the derivative of the inside just a 1, so it doesn't really change anything. Set that equal to 0. So when does 0 equal the root of x plus 4 plus x over 2, root x plus 4? And this should look a little familiar because I think we had something like this in our last video. So a great way to solve this is just to clear our denominator perhaps by multiplying everything by the square root of x plus 4. Because I multiply there, multiply there, and then multiply there, which the 0 doesn't really change, right? It's still going to be 0. So that's nice. So 0 equals, and then this times that is just normal x plus 4 plus, and then these cancel. So 1/2 x, just because I still have the 2 though. So then that's x plus 1/2 x is 3/2 x, and move the 4 over. And then we can multiply by 2/3, same thing as dividing by 3/2. So we take that times 2/3, and we get negative 8/3 equals x. Now that negative 8/3, only 1, but it falls within that value. So I could say my c value then is equal to negative 8/3. And again, it was guaranteed by Rolle's theorem because all 3 of the conditions were satisfied. Okay, so let's go ahead and I'll pause this video. If you want to try the next couple of examples and then check the video, because the next video is just going to cover the rest. So, and like I said, it's just an existence theorem too. So once you know it happens, then you still got to find it. And so there's always some algebra, calculus, solving to get those values.